Hello everyone, I'm Zhang Yujian from Tongji University. I'm talking about the seismic damage assessment method for single-layer steel latticed shells, considering multi-modal combination. First of all, I will introduce the background of seismic damage assessment method. Then I will introduce the equivalent static system used for damage assessment and the damage assessment procedures. Then I will use a numerical example to verify the effectiveness and applicability of the method. In the end, I will give some conclusions. Numerous damage index, including local damage index and the global damage index, have been proposed in recent years. The local damage index usually is strongly case-dependent and non-universally applicable to spatial structures. The most widely used global damage index is the modal vibrational information of the structure. Considering spatial structures work in a more complex three-dimensional way, the applicability of traditional global damage index in such kind of structure is further verification. Generally, the contribution of each mode response to the seismic response of spatial structures is scattered and relatively uniform, which is different from those of multi-story or high-rise structures whose seismic response is low-order model control. Therefore, single model information cannot be used to measure structural damage comprehensively. However, when considering multi-modal contribution, there are some problems as listed have not been well solved in the existing methods, which makes the damage assessment method based on model parameters unable to be directly applied. In this paper, damage index is established based on a specially designed equivalent static model. In this manner, the contribution of each model damage to the whole structure can be tracked dynamically with the accumulation of seismic damage. Based on the model pushover analysis method, the equivalent static load and the corresponding equivalent static displacements can be derived as shown. On this foundation, the structural deformation capacity or seismic damage degree can be assessed based on the difference between the equivalent static displacement of the original structure and the seismic damaged structure under the same equivalent static load. We use these two formulas to calculate the seismic damage of the structure. In order to verify the applicability of the proposed method, we use a numerical example as shown in the figure to evaluate the damage of structure under different seismic excitations. The numerical example is a cavity shell. Its span is 60 meters and its height is 20 meters. The figure on the left presents the damage development curve generated by the idea of selected 10 ground motions. As we can see, although these curves exhibit a distinct scatter due to the randomness of the seismic excitations, all curves still comply with the typical damage evaluation rules. We choose the damage development curve of 4 seismic waves and compare them with the structural displacement response curve on the corresponding seismic excitation, as shown in these figures. As we can see, the displacement response of the structure is greatly low in the early stage of damage development. When the damage index is greater than about 0.4, the displacement response increases greatly. Here are the comparisons between damage development curve and the structural plastic development curve. We use these two plastic indexes defined by the right formula to evaluate the plastic development degree of the structure. As we can see, after the structure is in the plastic range, its damage index increases significantly for the first time, which indicates that the damage development in this stage is mainly caused by the plastic accumulation of members rather than the nodal residual displacement. To further verify the applicability of the proposed method, 3 methods are selected as comparative methods, and the damage assessment results are compared as visually displayed in these figures. As we can see, the damage index value given by the FS method and the Shi method is equal or very close to 0 in the early stage of seismic damage development. As mentioned above, obvious plastic development has been seen in the internal members, and the residual displacement of the earthquake can no longer be ignored, which indicated that it is unreasonable for the seismic damage index equal to 0 in this damage stage. For the He method, because not all modes are considered, part of the modal damage has been missed, which may lead to more conservative damage assessment results. In addition, in the case of strong nonlinear range, the modal coupling effect of the structure will make the assumption of the modal superposition principle in linear range is no longer valid anymore, and the phenomena of oscillating changes will be observed in the damage index curve generated by her method due to these above reasons. In addition, we also verify the applicability of the method on the multi-dimensional seismic excitation, and the results are satisfactory. In the end, we can get the following conclusions. To avoid repetition, no more described here. Thanks.